Okay, I wanted to do another video here where I just do a quick summary of some of the stuff I've added to EvilVM, or at least the most significant things, since I presented it at NolaCon. So I'll start with the new transports. I had said in my presentation that I had a couple transport ideas, and I had ICMP code pretty much done and ready to go. So that is done and is available in the system, so I'll demonstrate that a little bit. And then I also have implemented SMB named pipes, which I think is a pretty cool feature. Each of these show up in lots of situations when you're pen testing a hardened environment, especially when you have strong firewall controls that really inhibit your movement into some particular protected space. So I've had a number of situations where ICMP was my only option. I could ping back and forth between my target network and where I was. And then also a lot of times 445 is the only port you have available on a target system, so SMB is a really great transport as well. Okay, let's get started with ICMP. So for ICMP, it works actually very similarly to the HTTP transport, because HTTP and ICMP are both stateless, so it's actually one of the larger transports. To use it, the first thing we have to do is build an agent oops, if I could spell. So we can just specify which transport, and then it needs to know what IP it needs to connect to, and that's pretty much it. So ICMP-I, this is the box that I'm currently using right now, and then it'll generate raw shellcode. We'll write it out to ping.shellcode, and that should give us a working ICMP agent. If you look in here, you'll see at some point in here, there we go. So we've got here the sections where it's importing the ICMP function calls from Win32. This is all written in assembly. In order to write these, I have to do them in pure assembly, because this is at the base of the language. The language doesn't even finish booting. There is no compiler until there's I/O. So having the transport working is a precondition for everything else. So that said, once we have an agent, then we can run our server. And then we have to run the shim, because the server only speaks reverse TCP. So let's run server, ICMP server. It needs to know what IP the ICMP packets are coming into. That way it can differentiate them from other pings. And then it needs to know where it needs to connect for the server. So once we have this, we are pretty much ready to go. Let's hop over. I have a script I use for triggering execution over with WinRM. So this is just a remote invocation. You could use WinExec, you could use PSExec, whatever you wanted to use for this. This is just one quick way to run it. What this does is opens up a little HTTP server and then uses WinRM to plant a PowerShell script that'll download this file. So we get that going. We can see we've got pings coming in. So similar to the HTTP transport, the ICMP transport has a 5-second polling interval by default. You can set that to whatever you want. So if you want it to poll more quickly, that's fine. But let's go ahead and do something actually useful with this. When we run with WinRM, we're running just in some process detached from a desktop and everything. So let's see if we can find a user logged in. All right, so there we go. So here's an Explorer process. Let's go ahead and load a module. So here's the inject module. This allows me to inject an EvilVM. It actually just takes the exact same payload and injects itself into another process. So what was that PID? 10332. We'll go ahead and inject that guy. And you can see that it works pretty quickly. We get channel 2. And once it finishes staging the rest of the core language, we'll be able to see that, in fact, this is a different user context. So each agent is assigned a different Crayola color based on its username and hostname and other things like that. So this is obviously some other user. So let's go ahead and switch to that one. And so now we have 2 concurrent channels. So each of these sessions are using the same payload, but from different processes and in parallel. So you can see we get 2 pings every 5 seconds down here. Let's do something useful here. We can see here we're the Josh user, not the Josh admin user that we used to launch it. This is one I'm particularly proud of because I've spent a good bit of time figuring out some interesting things to make screenshots work and make sense in the sort of context that I'm in. So let's just grab one. For now, it'll take a little while to download because the throughput with ICMP obviously is not as good as you would get with other protocols. Right now I'm using just a very simple sort of reliability where it sends a packet. If it doesn't get a response, it sends a packet again. So that means it can only ever be in the process of sending a single packet at a time. And I'm keeping them at 512 bytes because that keeps it well under any reasonable MTU that you might run into in real life. You could make packets bigger if you wanted to or something. But anyway, eventually we'll get this 154K screenshot. I wanted to do it this way though because it shows that the transport is actually fairly robust. So like here's a screenshot of the desktop, and we can interact with it if we want. With some other modules, I've implemented some keystroke injection and other stuff. I won't do that now. This is mostly about just the transports. But this shows that we can have a couple of concurrent connections. This is all ICMP. So in fact, if you watch it here, the ping's coming in, and then I'll run something here. So we'll just list the words, and we'll see that there's a little flurry of additional activity. This would be a bigger packet, yep. And then that gets us our data in. So it works pretty well. I've had a couple of occasions if you get lots of sessions, or like if you had a stale session that died or something, occasionally there's a little confusion. So there's a little improvement to be made to it. But for most circumstances, it seems to be working pretty well for me. I've had it run overnight successfully, and with things going on like key logging or something overnight, and seems to be stable. So I've been pretty happy with how it came out. Okay, so let's check out the other one. So the two transports that I've done so far are ICMP and SMB named pipes. This comes in handy, especially when you're compromising someone in a protected zone, like say it's a sensitive area of the network, and you've gone from the uncontrolled space to the controlled space. And a lot of times the firewalls in between there will be very restrictive. You might have only what's strictly necessary for business use cases allowing you access in. And sometimes that boils down to this one guy needs an exception so he can access a share on this one box in the target zone. And so when 445 is all you've got, then 445 is what you have to tunnel over, and that's where SMB tunneling can come in handy. Especially, so just imagine in that scenario, you can't make a TCP connection back. Maybe they block ICMP, like my last transport we talked about. So for whatever reason, sometimes this is the only option that you have, and works quite well. I'm able to use the Ruby SMB package. It's a gem in Ruby for Metasploit. Rapid7 originally wrote it. It is actually its own gem, though. It's not strictly bound to Metasploit, and it's an excellent implementation of SMB. It's got a couple quirks I had to learn along the way, but it turned out to be quite sufficient. So to get started with using this transport, we have to generate our agent. And as before, we've got a couple options for specifying how we're going to do that. So the first thing we need to do is specify the transport named pipes. Is it plural? Yes. You'd think I could remember since I came up with it myself. We'll call the pipe just something nondescript. If you make this too descript, then it ends up being kind of obvious in Wireshark. I'll show it in Wireshark in a minute once it's running. We'll generate shellcode, write it out to pipes.shellcode. All right. And then from here, we can just run the server. And we have a shim for this one too, but the shim works differently. So in this case, it's more like a TCP bind. We have to have the agent running first so it can host the named pipe, and then we'll connect to it. And then this shim is a client on two ends. It connects out to the named pipe, and then it connects to the local server, and bada bing, bada boom, everything works. Which means we have to invoke it first. So let's go ahead and do that. And actually, yeah, we'll just do it this way. So we've got this one we use for activating this shellcode. And this time we'll switch it. We'll do pipes. So this one, it'll execute and it'll host on that pipe. And hopefully what that means is that we can now connect to it. So we need a few things here. We need to know where we're going. We need to know the name of the pipe. B, C, D, E, F. Did I add a G to it? I did. And we need some credentials. So that'll be there. And the delay is, so this is an optional parameter. By default, it's 5 seconds. It happens that from the client side, there's not really a good way for the other side to notify that there's something available, at least with the Ruby SMB library. I'm still investigating whether there's a way not to have to do polling. But the way I'm doing it now is basically, if there's no data to send at least every 5 seconds, it's going to do a peek on that pipe and see if there's data to read. I found with Ruby SMB that if I just went to read a byte, that I ended up with some weird issues, and I don't know if it's Ruby SMB's fault or if it's something else. Whatever it is, the polling seemed to work a little bit better for me, and hopefully I can improve that in the future. We'll see if there are options. So once I connect this, we should start getting data. This looks very similar to the other shims. We just see every packet that comes in and every packet that goes out. And so we can interact with this, just like any of the other shells. I thought it'd be worth showing this one in Wireshark though. So let's bring Wireshark over here. I'll put it up here on this one. So we can see the traffic going through, and here you can see the polling behavior. I'll run something that'll generate some traffic, and you can see what that looks like. So there we can see some larger packets coming in. Now this one doesn't use encryption yet. I need to add another layer on top of this that'll add encryption. But part of the reason I haven't done the encryption on this one yet is that I've had some thoughts about how I want to restructure and refactor some of the transports. So, that should be coming. It's on my list for the future. But you can see all of this is coming through on TCP 445 right there, and just a bunch of normal SMB traffic. And just as interactive as ever. So we can use it. So that's just a quick tour of the couple new transports, and also I guess showing some of the new samples that do some nice PostX stuff. I'll certainly be doing some more. I have a couple ideas in the queue for doing some intro to Forth itself, so that how the code looks for these things should make some more sense. For example, I did the screenshot. It's been really fun learning how to improve and develop the language so that it gets easier and easier to write these things. So for example, here's support for structures and other things. And my process for writing this is actually something that I think is kind of fun. So I want to do some videos where I go through some of this material and just show, this is how I can write this stuff. This is like right here, this is the function that does a screenshot. And it's basically a direct translation of a Stack Overflow post somewhere, and turns out not to be that big of a deal to make a lot of these things work. We have to get over the syntax a bit. I'm hoping to do some Forth language videos coming up soon. And I think that's it for now. Thanks for watching.